Okay, so welcome everyone. This is week 8, and Weixin is here just in the nick of time. So you can see we mentioned you on the Slack channel. Okay, so we'll go ahead and start. So just to keep everyone in the know, we have from our 6101 course, again, if you look at the schedule, I have to do this every week, is remind you that we actually supposedly already had our abstracts due. So if you don't have the abstracts, they don't go to projects. Actually, they go on to the iSteps website. So if you go to iSteps, 14 steps, all that. Oh, like that. Events. 1, 12, 13, 14. Where did you saw it?
Yeah, 14.
14 is on the top. Oh, thank you. How come I can't see? That's pretty bad. So if you go to this and you log in, you should be able to find your project here. Okay, and you should have gotten an email from the system. If you haven't, let me know. You can let me know on the Slack channel or whatever, and then you should be able to update it. So right now, I think most people haven't added any abstract. There's only one team that did, and you can see it here, right? So it's on the main page as well as on the login page. So you know, even if you're doing a homework assignment, you can sort of summarize it. It's probably not a great idea to have a project named Homework 2. So I just replaced it with the title of the homework assignment. So I know some of you are doing homework from Sergey's class. So just do it that way. Okay. So that's what I wanted to say about the class. It's just that we do need your projects and abstracts soon. Okay. The second thing is, you know, in the upcoming weeks, you know, from today is week 8. Week 9, 10, 11, and 12, and 13. We don't have to stick to these lectures. Okay, again, all of you in that particular week can decide whether you want to take on this suggested lecture. So if there's another lecture by Sergey that you wish to do, then you can do that. And then internally, we have been discussing here before the broadcast went live that maybe we would pick other problems like, say, for example, AlphaGo or AlphaZero. Those are papers that are in sort of like the popular science domain. So it might be nice to construct a lecture or scribe materials on that. I think that would be useful for the public and also useful for us because there's no a lot of resources on those yet. Okay, so if we wish to do that, we can take, for example, week 12 or week 13, depending, again, on the presenters that are due that time to do that. I think, for example, inverse reinforcement learning and exploration are probably strong enough lectures that we probably want to cover them anyways. But then parallelism and RL system design, well, that's sort of practical. Maybe that's useful. Advanced imitation and learning by the whole problem of saying advanced, I guess AlphaGo could fit in there. So really depends on what you guys want. Okay, so enough of me ranting. So I'll turn it over to our presenters. I think Vikash is going to start first. Okay.
So we're going to talk about learning policies by imitating other policies. In the previous lectures, we have learned about learning from humans, but now we're talking about how do we learn from policies. So far, what we have learned about in the previous lectures, we learned about how to train global models, how to train local models. But what if we want to learn a policy? What's the benefit? Potentially, they are faster to learn, or also they generalize better. So, what is one way of learning them? In previous so one way could be we learn a model and then back propagate that to a policy. So we start with the base policy and then try to learn a dynamics model using some model of trajectory optimization algorithms, and then back propagate that and then try to optimize the policy, and then we iterate. So what's a potential problem which could encounter? So one of the problems would be like, if you do this way, initially we'll have like big gradients, and then as we and it gets smaller, and it's something similar to this, where uh, even a small change can have a very large impact at the later time. Uh, this is very similar to what happens when we do learning and recurrent neural networks. When there are long chains, we have issues of vanishing and exploding gradients. So this is something similar to that. Uh, what could be another way? How about collocation methods? I think we have learned about this in previous lectures, which is modeling this as a constraint optimization problem, where you're minimizing a cost function given a dynamics model. In this case, we can actually extend this by adding our policy as another constraint to this. So what we really want actually is to learn a policy. So how do we generate trajectory? How do we do trajectory optimizations? We can actually relax this constraint a bit. So how do we go about doing this? We have also seen this in the previous lectures using dual gradient descent, where you have a function which you're minimizing given a certain constraint, and we'll create a dual of that function using Lagrange multipliers. Uh, so how does this work? So this g lambda is our dual function, and x star uh, uh, minimizes this dual function. So if we calculate the gradient of this g function with respect to lambda, what we get is this is something which was explained by the professor later, where you get this equation where, since x star is minimizing uh, this function, this part of the equation becomes zero, so it doesn't matter what we are doing here. And the derivative of function g with respect to lambda is actually the derivative of the Lagrange with respect to lambda. So what we do here is we find x star, which minimizes this function, and calculate the gradient, and then modify lambda accordingly, and then iterate. There's another addition to this which stabilizes this function, is by adding a penalty here, uh, which is this. So how do we how do we enforce this trajectory optimization constraint? So this is our function and the augmented function here with the penalty. So what we try to do is first try to learn a trajectory using trajectory optimization algorithms, and then try to learn the parameters with stochastic gradient descent, and then update lambda and iterate. So for the deterministic case, uh, the, uh, the cost function is this. So in order to generalize better, what we could also do is to uh, learn from multiple trajectories, and then update our theta stochastic gradient descent. And this generalizes much better. So now
Okay, that was fast.
We want to discuss it a little bit before we conclude Vikash's part of the lecture. Any questions that we want to ask, or that the presenters themselves? I guess you guys watched the whole lecture, right? But do you have anything to say about that? So about the penalties, is it clear what the penalties are doing? I'm sorry, I was not paying too close attention because I'm editing some things on the YouTube channel.
Why the additional quadratic loss?
So there's a quadratic loss rather than just a difference
Say
value.
something about stabilizing. Why is it stabilizing? Is it really the action? Right?
Yeah. So this we can let's say we ignore the first term. So after the CT, this is like a mean square error function. Right? We could also learn just by this, but we need a very high value of p here. So adding this term, one of the things which you mentioned is, let's say the Lagrange multiplier does not have a stable value. I don't know what that stability means here. And this helps in stabilizing the learning.
Right, so you have a normal difference loss as the first term, right,
Yeah.
over all the time steps, and you have a quadratic loss on the second one. So the quadratic loss, do you guys remember what he said in specific? I mean, there's got to be a penalty for not following things very closely, right? But why the quadratic loss?
And the first one already does that, right?
Yeah.
The first one does a difference, but it's not quadratic, right?
It's not quadratic, but it's from the Lagrangian, it's from the formulation.
Yeah, they're both for that reason, right?
Yeah.
I think there was, if I recall watching the video, I think there was exactly this question asked by a student, right?
Yes.
Somebody asked why there's a second.
The quadratic term, right? So
Yeah.
I think like what he mentioned was that like when you initialize like the lambda, so when you initialize it, right, at first it might be small, or it might be the wrong. So at the first few kind of steps, it might be wrong, or it might be too small or too large. So then when it's too small or too large, like your constraint is not properly enforced with just that first expression itself, the non-quadratic one.
This
yes,
one, right?
Yeah, wasn't properly enforced. So to kind of get around that problem, you add this, you add a quadratic term, because that kind of keeps the constraint from being violated too much. Because it's quadratic, like the cost will kind of increase like quadratically, and then that keeps it from violating it too much. And then here the rho, which is like the p thing, it is kind of decided like heuristically. So it really depends. Like what happens is, like I think he said like if the cost, if your cost is going to zero, if it's going to zero, then you keep the current p. But if your cost suddenly start to increase, then maybe you want to increase the constraint that. So in that sense, it kind of keeps it more stable, because it's mainly for the first few steps when your constraint is not really being properly kind of enforced. Yeah.
So, then do we need the linear term? Can we just get away with the quadratic term?
Yeah. So it was mentioned that you can just kind of, some people just remove the linear term, but then when they do that, like your constraint is not really properly enforced, and it basically requires like your rho to approach infinity for your constraint to be really strictly enforced, right? Yeah. So in order for your so you can remove it, like people do that. They say that people sometimes do that to just kind of help them kind of and then if you do that, so if you remove the linear term, It's called penalty method, apparently. I think that's what he mentioned.
Okay.
Like if you don't remove it, it's augmented. So if you remove it, it's called a penalty method. And yeah.
Okay, so maybe our scribes can go figure out whether that's correct. You know, I'm gonna go look at it too, see whether we can find cases of this, whether a squared loss versus a monotonic linear loss has different names. I mean, in this particular setting.
Yeah, but that's called a penalty term. So I think the quadratic term is called a penalty term. So yeah, sorry.
Okay. Yeah, they're both penalty terms, right? Both the linear and the quadratic term are penalties. Those of you online, did you watch the lecture? And if you did, do you have any comments on this part about the two penalty terms, the linear and the quadratic? Okay, so we'll go ahead from that. So thanks, Vikash, for the first part of the lecture.
Actually, like I have clarification, like so where was it? Like so these collocation methods, right? This is basically like I think we covered it during lecture 10, like the controller and planning section. Like you mean, so basically there's this collocation method and there's the shooting method, and then for the collocation method, like what happens is that you also minimizes it over the states. Okay, so I'm a bit like confused as to whether so I know like the LQR that we mentioned, the minimizes like the cost function with respect to only the actions. So I'm just a bit confused whether the iterated LQR, is it a collocation method or is it like a shooting method? Does anybody?
So the iterative LQR, does it depend on the state?
But because what happens is like I think, let me see. Yeah, she have the slice here. Yeah, this is the iterated LQR. So I'm not sure whether this is like collocation or shooting, consider shooting. Because for the LQR itself, I think what happens is like the transition function is actually deterministic, and so actually like if you give it a sort of x and ut, then it's always going to be like a deterministic next state. So I don't see like how you can kind of minimize over how you can kind of pick the states and at the same time do this. Anybody have any thoughts on this?
Any thoughts?
No, we can just.
No, I mean, these are good questions, and you know, we shouldn't really think about just lecturing. If we don't get any understanding out of the lecture, it probably doesn't help anyways. So I mean, we can try to discuss a little bit and see whether there's any help that we can get from anywhere else. So I mean, you guys are also welcome to try to Google or whatever while you're doing that, and then try to figure out whether there's something specific that we can get from other people's slides. So maybe we can spend a couple minutes trying to figure that out. It seems like we might be proceeding. After we finish the first part of the lecture in 5 minutes. To LQR.
Yes, Wi-Fi is a bit slow today.
Oh.
Is it? There's this guy, Jonathan Hui, who keeps on posting on Medium
Yeah.
about reinforcement learning. So we're hitting off his posts in certain ways.
There's also something on Google.
Yeah, you can post it in the Slack. Previously, we used Slack quite a lot during lecture to share information and put up things. Okay, so while all of us are on our various laptops and figuring out, Nan asked a question. Sorry, I didn't get the question about LQR, so maybe Yihui, you can repeat.
Right. So I think in general, like the question is just whether like iterative LQR, whether is it a shooting method or is it a co-location method?
A shooting method or a collocation method, where the shooting methods just generally model the action.
Yeah, only the action. Yeah, and the collocation minimizes over the actions and the states.
Optimizes over actions. Collocation models. Is both actions and states. So Shenting, you saw something?
Yeah, I'm trying to load the PDF, but the preview I got, it says you can run it both as a shooting method or as a collocation method. It's just a different way of executing.
Okay.
I'm still trying to load the PDF. It's really, really slow today.
Yeah, let's see whether we can go to. Let's see whether we can pull it up. I need to pull up my share screen. Oh. Okay, and then there was this one from here. So you can do that. Okay, that shows something. This says shooting methods. Was it here or further down? Okay, I think this is the slide you're referring to, right? Iterative OQR versus sequential convex programming.
Control feedback for swapping one. Control feedback.
It's one. Feedback from solving one.
What's one?
One, okay. I think we have to go back. Where's one? Ah, okay.
Oh, that's one.
We know how to solve. Okay, I'm going to put this in Slack and see whether we can see the Slack. And you'll have it on Slack. Then I'm going to scroll down. Say. So I think this is one, right? This looks like the same set of equations, right? So minimize, the cost over states and actions. Am I reading that right? Subject to the states and the actions being in the set of states and actions available, I guess, from the current policy.
So there's only one line that's different, right? Whether you execute it or not.
You mean this part here, right?
Yeah.
What's a feedback controller? Because it's kind of showing a sequence of movement.
Did I miss anything on Slack? Anyone have anything to say about it? Okay, I guess not. So I guess we don't have a good answer for this yet. So
Okay.
maybe we can keep your question for the scribes, and then we can go back to the lecture, watch that part, and see whether we can find a good answer to that. So yeah, you can go back to your screen, which I think we can do by back to yourself. Then turn this off. Yeah.
Okay.
And then present. Yep.
All right. So let's continue. Right. So we just do a kind of quick recap on what we have covered, like so that we can build it up towards the stochastic GPS, and to just kind of starting off, like in lecture 10 we learn about like optimal control and planning. So this is the controller, which essentially what it does is that if you give it a known if you give it a known dynamic, so if you know your dynamic or your dynamics, which is the function f, you can actually kind of find it can output a policy, not optimal, but a policy for you to optimize the with regards to the cost. And for iterative LQR, be non-linear, and your cost can also be non-linear. But what it does, it kind of use a first a Taylor series expansion, and then it approximate your non-linear dynamic and cost using linearly using Taylor series expansion. And so yeah, so the big thing about this is that it assumes that the dynamic is known, yeah, and it approximates it, like even when it's non-linear, you approximate it with a linear function. And so then the question comes, like whether or not so LKR gives us an output which is this equation over here, and then the question is, like, should we just follow this
equation?
This one.
Okay.
Right here. It gives this output, like which relates like everything which relates the state to the action that you're supposed to take. So it kind of gives you like, oh, if you're in this state, this is the action that you take, and this UT with like this caret sign over there, and that's just your Taylor series expansion, and you're expanding it with this fixed constant. So yeah, so it gives you this action that you're kind of, it recommends you this action that you should take. But then, like, do you really want to just follow this action that it outputs? And it says like, and we kind of go through it and say like, okay, maybe that's not really that nice, because what happens is that if you only take this action every time you see this state, you're not going to see a lot of different sample, like different states So you're always going to be like following this kind of path, and you want to kind of add some noise to the action that you're taking, and that's how we come about this term, which essentially says that, like, given this current state, like the action that we're going to take is going to be stochastic. Like this is going to be a distribution over all the actions that we take, and then we kind of kind of model it as a normally normal distribution or Gaussian distribution with a variance that we get to choose, right? So yeah, and so we choose this as our controller to basically, given a state, we're going to take this action with based on this probability distribution. And so there's still this assumption that, like, we got to know what is our dynamics, right? And then how do we actually like kind of find that out? And then because the dynamic in real world can be very complicated. It could have been like, it's some unknown function. It can be really complicated. And the idea was that, right? So instead of trying to model, like try to really guess this dynamic, we just like, because we don't know this dynamic, we don't know the real dynamic, so we're just gonna assume that it's gonna be a normal distribution, and it's gonna be a normal distribution, and what we can do is that we feed like each we fit basically the current state and the current action with the next transition. We feed it using a linear regression, and you can see that this is actually like this just solving a ordinary it's just solving ordinary least square method, in the sense that like the x and the u are your variables, and the at and your bt are like your coefficient, and then the c is your kind of like
Your bias.
yeah, your bias, right? So and we know that, like, or maybe we know that in ordinary least square methods, we kind of assume that like sometimes the noise, that we assume it to be normally distributed. So the form looks exactly the same. So if we assume that basically the dynamics is gonna be a Gaussian, we can then kind of model it using like linear regression, and we get this nice right, we get this nice approximation for the gradient of our dynamics function with respect to x and with respect to u to be approximately a and b, which is essentially your coefficients from your linear regression. So these are kind of covered like in the slides for lecture 11. And so the question is, okay, so right now we are approximating the dynamics using linear regression. And so, well, there's a problem with this in the sense that, like, for example, if you are feeding your linear regression with states and action that's, let's say, in the range of, let's say, 1 to 10, and then what if I want to predict for my states and action that's in range, let's say 1,000 or 1,000,000, right? But you know that you are only doing like linear regression, and then because you're training your model on states that 1 to 10, it's not going to be nice if you kind of use it to predict for states 1,000 or 1,000,000, which is very far away from the data that you're actually training with. And so we actually want to control for this by asking our model to kind of like, okay, so our controller takes in this dynamic that we learn, and then it kind of outputs a better better action to take. And then so you kind of want it to kind of not be so to kind of not drastically change our trajectory so far, because we are not very certain about trajectories that we have totally never seen before, but we are certain about in this region of the state space and the action based on our linear approximation, we are roughly more certain about where they're gonna be, and then we take this into account by adding this k-out divergent terms, which essentially measures the closeness between your new optimal trajectory that your controller is gonna be able to output and your old trajectory. So instead of this thing is not going away. Okay. How do I get this?
Yeah, sometimes it doesn't move. You can press on the, yeah, it'll disappear by itself.
Yeah, so the equation in the red box, instead of just minimizing over the expected cost over the time step, we add in a constraint such that like the output trajectory has got to be somewhat close to our old trajectory. So by doing this, we make sure that whichever like the controller doesn't abuse our linear approximation of the dynamics and kind of output this totally different trajectory that is based on an approximation that's so far away from it. So does anyone have any questions here? I hope I'm not confusing anyone.
So let me try to recap, and please tell me whether I'm wrong too. Earlier, we were talking about making sure that the new policy doesn't deviate too far from the old policy, right? And so we want to keep the new policy that's created by the model fairly close. Now we're saying something about the trajectory, the rollouts as well. Is that correct? So we're saying the new rollouts that we're going to investigate, they need to be fairly close to the existing rollouts that we actually have sampled, so that when we are doing a linear approximation of the value of that state or action, then it has to be fairly accurate, right? If the trajectory is like wildly off, instead of like, let's say the original trajectory is the one on blue on this slide, right? Yeah. and then the new trajectory that we're trying to make is the red one, right?
Yeah.
But instead of like taking one of the black ones that's far away, right? Is that what we mean?
Yeah, it could, like, it might have estimate, like, so the blue line is your dynamic, that like your linear approximation for the dynamics, right? So
Okay.
so your controller may be like, hey guys, like if we were to reach this state, it's gonna be so much like more all right, so much better. So for example, let's say we take the height as the reward. If you reach here, there's gonna be so much reward, but the green line is your actual reward. But it's because we're using a linear approximation, so we don't actually get to see that the real rewards is actually so low, but then based on linear approximation, it's going to be so high. So maybe like your controller will just kind of abuse the fact that you're actually using a linear approximation and just go here, right? Yeah, and that's what they want to avoid. So they want to kind of avoid trajectories that's very far away from where we're actually feeding the data at. So we are actually feeding most of our data here, right? So we have seen data here, but we're not seeing data here. That's why we are feeding a linear. When we feed a linear approximation, we kind of get this sort of straight line, right? So you don't want it to kind of create this new line that goes from here and then goes to this low end over here, and then I don't know where it goes, because we have never seen that before. And then whatever prediction we make about the dynamics that's happening here, we are definitely not certain about it, because we have never seen the data point before. So we don't want the controller to really abuse this fact, right?
So when we say that the KL divergence of a trajectory shouldn't be too far away, it's basically some type of confidence interval over the, I don't know, is it X or Y? The slanting axis that's going this way.
That's the state. Yeah. Okay.
That's the dynamics.
Yeah.
Right?
That's the state. So this, I think this is the time.
That's the trajectory. Right?
Yeah, that's the trajectory. Yeah.
And the vertical, you're saying here is the reward function.
Yeah. So for it, yeah.
The evaluation of the cube.
Yeah. So you just don't want two lines to be very different, drastically different from each other, because like you're linearly approximating this, and you're kind of sure about data at this point because it kind of fits, but your approximation is not going to hold for data at this point because you're using a very simple linear regression. Right. So yeah. So does anyone have any other?
Well, the explanation of the diagram was very helpful to me. I couldn't parse the diagram very well either. Yeah, I understand what the axis where the arrows are going has to be the trajectory, but I wasn't so clear about the horizontal axis in the room.
Yeah, I think they're the states. Yeah.
Okay.
Yeah.
So the dynamics are being approximated by the blue line, and you're saying the actual dynamics that might be created by the system is that green line.
Yeah.
Or the sample.
Yeah. Kind of like, yeah. Well, you can think of it. Well, I think it's actually kind of hard to, because actually you got to take into account of your actions. So if I want to kind of measure the dynamics, but it's kind of impossible to visualize for me. So yeah. Okay. But like in a matter, like just crudely, you can kind of think of this as that dynamics that we are approximating, and then we are really not sure about what's going to happen, like because so we basically don't want whatever trajectory that the controller is asking us to do to be really far off from what we have seen, because that's where the data we have feed the dynamics is at. So yeah. So with that, so I guess that's where all these kind of come about, and then you get to see like this. Okay, so the stochastic GPS, I think is called the stochastic GPS. What happens is that it adds a new term, obviously, like because right now we are not just using the controller. We have another we have a controller. We have our controller, which is this guy, and this guy is basically seeing your current state, is giving you an output of your action that you should be taking, and it's normally distributed because we kind of want to see, like, we kind of want to explore a bit. So there's a Gaussian, and this is just really from the controller page, and we're just pulling it over here, and we have the dynamic is not really kind of So this is the controller output. Yeah. So to kind of really so first step we optimize the trajectory with respect to the dynamics is actually implicit in this. I think like the expectation itself. So we kind of optimize our whole cost function with this KL divergence. So we don't want our new trajectory to be very far away from our old trajectory. So we have explained like the motivation for these KL divergent terms, and then you get to see like this C is different from the pre. This C is different from this C because like it has this curly sign over there, and that's really because right now we have this additional component to this whole thing, which is the policy, our policy, right? Yeah, which is our policy. So we have a controller, we have a dynamics, which is implicit inside this expectation, and we have a model that's really trying to learn the policy. And so the main part about this is that what we want to do is that we want to basically optimize our trajectory. We want to optimize our trajectory with this controller, but we want the controller to only kind of optimize it over the possible trajectory that our policy can express. So we don't want the controller to, because the controller can optimize it over like a few millions trajectory, but it doesn't. It is not going to make a difference if our policy is not able to kind of represent them, right? So that's why you have this. You kind of have to add this constraint over here to make sure that when your controller is optimizing the trajectory, it's also taking into account of the trajectory that is really able to be represented by your policy. So right, so this term over here is the cost. Is the cost with the curly sign, and then we use previous method that was covered in the first half of this lecture, which is the multiplier, that you can just kind of use the multiplier, or the augmented like Ranjan, which is the one with the penalty term, or rather the penalty method. Oh yeah. So you can use whichever you want, and then you convert this into the cost, and then you feed that in here, and then you optimize your trajectory using this is what is optimizing using a controller, and then after that you take this whole you take it, then you optimize it with respect to your policy, and then you enforce the constraint. So this is the main idea, and then like the whole workflow goes like this. So you have your robot, and then you collect some data, and then trajectories, and then you kind of train your policy on these trajectories, and then you feed a dynamic model because your iterative LQR needs that dynamic model, and then you train your controller. But at the same time, you train your you improve your trajectory using the controller. At the same time, you constrain it to kind of only pick trajectories as or rather actions as that your policy model can represent, and that's what this arrow is. And then you keep repeating this process. Is this clear? I hope I'm not confusing anyone.
Comments?
What does GPS stand for?
Guide. I think it's guided policy search, but like most of the slides, he used a lot of short forms without any explanation what it actually stands for. So I'm not exactly sure, but I think it's guided policy. Oh yeah, guided policy.
He didn't say GPS. He said guided policy.
Yeah. He said guided policy search. So I kind of assumed that it's guided policy search, but yeah.
Yeah, there's a blog post or something about that also on Slack.
Okay, so right, so something that so I continue.
So there's a question by Nan. What's the difference between policy and controller here? Nan, do you want to elaborate? You can unmute your mic and talk. And can we hear you? Let's see.
Can we mute him? No.
He says sorry, I can't talk.
Oh, okay.
Okay.
All right. Never mind. Maybe he's in the library or something.
So wait, do we understand his question?
So he wrote on Slack, what's the difference between policy and controller here on this slide? I assume you're talking about this slide with the...
Are you talking about this slide? or the previous slide.
He's typing. This one, I'm
Oh, okay.
confused here. So maybe you want to step
Oh,
through the
this-
diagram of
yeah,
it again.
okay,
And
okay,
then
okay.
mouse
So-
go through it.
Right. So a controller basically from lecture 10, what it does is that it outputs a action given a state, but it requires you to have the dynamics, which is your transition probability, basically how your world works. Like if you are in this state and if you take this action, where are you going to end up next, right? So that is your dynamic, and for your controller to work, it requires knowledge of this dynamic, like how this world actually works. You need to feed that into your controller, and then it can, based on this dynamic, it can kind of judge like what is the best action that you can take. So that's what it is, and then based on that, it kind of improves your whatever you're doing, right? Whatever trajectory actions you're doing, right, it improves upon that. And so just now when I was talking about like the policy that I was referring to, I guess is you don't really need the dynamics, but what it actually learns, it takes in. Right now it's O, but you can see, okay, so O is observation, but it can take in either observation or you can take in a state, and then it just looks at the state and it tells you that, okay, you're gonna be taking, you got to take this action, but it doesn't require you to kind of feed in knowledge of how the world works. It doesn't require the dynamic for you to really be training this model. It just kind of see like, okay, like it's supervised learning, right? So every time you are in this state or in this, or you see this observation, okay, your trajectory, your this guy does, he actually tries to learn like what your controller is doing, and that's what, okay, that like in general, that's what this whole lecture is going to be about, like learning policy by imitating other policy. And this other policy that we are imitating is actually the policy that's being output by the controller. Yeah. So we're actually trying to learn what the controller will do. Yeah. Am I being clear here?
I think that's pretty clear.
Okay.
Yeah.
Why is there an arrow between the train box policy and the input box?
Right. So this actually comes from, I think, the constraint that this constraint here, which actually it just enforces that like when you're doing the controller policy search, right? It actually search over possible policy that's being output by your this model. It doesn't just run with policy that this model can represent. So yeah, I think that's the idea. But it was this topic was covered really fast by the prof. So yeah, okay. Okay,
Yeah,
so
that's good.
Okay, moving on. So a trick that was mentioned was called an input mapping trick, which the main thing here is that like during training, instead of feeding to your model the underlying state, which is xt, you can actually feed it the observation. So your observation actually comes from xt, right? So xt is your latent variable. Sometimes you can't observe it, and then sometimes you can't observe it. So instead of learning with xt, you learn with observation, and then so essentially that's the input mapping tree. So you give your model observations rather than latency. Okay, so I mean in a sense, so because okay, so your controller needs that underlying xt, right? So that's why your controller needs that to output the action. So your controller needs it. But when you're training the model, you don't really need xt. So you can just feed in observation, like whatever, like you can have xt here, but then like observation comes from xt, so you get like a function that gives you the observation, and then you just feed it into your model that you are trying to make, and then use the label that your controller outputs to kind of match that observation with the action. I think that's what it's doing. I think that's what this is doing actually. So at test time, because at test time what this diagram actually trying to explain is that at test time, because you're not actually using your controller anymore, so you can kind of just feed in your observation and get an action. So you bypass the whole controller. So you don't need your xt, which is your latent variable. Yeah. Ooh. All right. So then there's a break. Should we take a break or should we continue?
Are you continuing? Or?
I can continue, but it's just yeah.
Okay. Well, why don't we take a 2-minute break?
We have a luxury of time today, I guess.
Yeah, a little bit.
I think the next part is easier.
There's quite a lot on the input remapping, right? He talks quite a bit about that through.
He showed. I think he showed something like yeah. I mean, from my understanding is that like it's essentially you're training your model with observations rather than the state, because at test time you don't really have that.
You don't have the state information. You only have the observables, right?
Yeah. So he talks about like how the robots like at this slide was like when during training time, like the robot has to kind of hold that box that it has and then rotate it. So you kind of meet that, but then like at test time, it doesn't have to be you can be holding the box or you can be just placed there, but you can just kind of do it. So I don't really get like how that is the state, but yeah, that's the idea. But it's essentially like during training time, your model is still like there's a camera, so the camera is still like looking at it as like an observation of that box.
Was it observing through the actual thing or through the simulator? I thought that a lot of the input remapping was because of simulation. No, I think
this
is actually on
the actual thing. Yeah, I think it was
device.
So it was showing the robot that's doing like some turning thing and it was like looking at it. So like. Line like the hand, so during testing they just use the camera, right? They don't need the hand to kind of control it. I don't know, I wasn't really sure about this, but yeah. Yes, man.
So yeah, if you find anything that's related to input remapping or things of that sort, we can try to figure it out a bit more. Most of that terminology seems to only come from this course.
This course is too at the forefront of it.
That's why we're doing it, right?
Yeah, there was the other course that was so much easier to follow.
Which one was that? The Silver course?
Yeah, oh my god, David Silver.
David Silver's course is, I think, a bit more basic and straightforward, right? It doesn't have the deep part of the system. Right?
It's like way more, it's way easier to kind of.
Right, which is why Weixin said, okay, maybe we use that as a prereq for this course. And I think most people haven't watched it. I haven't watched it, but I certainly will go back and watch all of the lectures for that.
I watched the first half. I think it helps a lot at the start, especially like when it goes through. Actually, like for that course, like I think it's more concrete in a sense. Like he quotes a lot of examples, and he really runs them through like step by step to kind of show you like how the algorithm works.
Have you watched the Silver lectures?
Some of
them. Yeah, I think as a professor, I'm watching more and more other people's lectures to teach my own courses. It's funny.
Okay, shall we continue?
Yeah.
All right.
You're ready.
So then we move on to a different kind of learning policy. To learning other to different way of learning. That is in lecture 1, and this is just an introduction. Like this paper uses that, and the algorithm that was used in this paper goes as follows. So you get for your current state, right? You run a MCTS, which is the multi-color tree search, which is a controller. Which means that it needs to know the dynamics of the world, and then it gives you a recommended set of action. It's essentially a policy. It's a model that gives you a policy, but it requires the dynamics of the world. And so based on this action, you create a data set with the current state and this action as a label, and you call it data set D. And then when instead of executing the recommended action, you execute what the action that your current policy will take, because the whole point of MCTS is actually serve as a guide to kind of guide your current to kind of train your current policy. So you don't want you want to learn the labels for the states that your current policy will go to, and not learn labels for states that your current policy will definitely not go to. And that's why when you're taking action, you're actually taking action that will be taken by your current policy. And so then you see so essentially that's the reason why you're doing this. And then with that, you update your policy using this data set, which is essentially what your tree search will do, and then you run the whole thing over and over again. There's two loops, so you can run this inner loop first, and then every certain number of steps you update your policy. You don't have to update your policy every single time. You can update your policy, after a few runs. So that's generally like how Dagger is being used. And so how is this similar to Dagger, and the way it is really as a general framework? What it does in Dagger, you train your policy using this human data, which is essentially, I guess, labeled by human, and there's observation, and there's your action that human will do, and then you train your policy based on that, and then you run your policy, and then and then it gives you this new set of observation. It asks your human to label this observation, what you will do here, and then you kind of add them to your database and you train again. So that's Dagger, right? And then this thing, instead of asking the human to label your action, you're asking the machine, the controller, to label your action. So yeah, so that's the main big difference. That's how they are kind of improving over Dagger. So you don't really have, the human don't have to work that hard to label it. And I guess there's a problem here, and the big problem with this algorithm is that ultimately it's still on policy, and it's gonna be a problem when the policy that you start off with is making really ridiculous choices. For example, if you're training a policy to kind of drive your car, you can't possibly let your policy run wild in crash a few trees and cones before you actually kind of learn what it's supposed to do, right? So sometimes you have a policy, but you don't really want to run it exactly in the real world, because it's safety concern and whatnot. It's very costly to kind of make that. So what they do instead is, are we able to kind of to kind of bypass that a little bit? And so this is the plateau algorithm, and it improves over the previous algorithm by instead of running the policy directly, you run a kind of modified version of the policy. So how do you actually modify this policy? And there's a lot of ways to modify it, I think was mentioned, but in this particular example, they're just using a simple stochastic policy, which is a Gaussian distribution policy, and then they are modifying it by finding by minimizing by factoring into this new by minimizing over the expected cost plus a KL divergence between your new policy, which is the one that you're kind of running, and the policy that you will have run if you just train on a data set. So essentially what this does is that, okay, I want to kind of improve the policy that my data is giving me, but I don't want it to be too far away from what from the policy that my data is giving me, because ultimately I want to kind of I want to be able to reach the state or near the state that the policy that my data is giving me to kind of see what I can do, because controller to kind of want to see the state, but I don't want it. But I'm weighing it between the cost of going to that state and how much my new policy kind of diverges from from the policy from the model. And so the example goes like this. Like, for example, the green arrow is the one that is being output, like the action that the model that you train from the data set D is telling you to do, and the red arrow or the orange arrow is the one that is actually improving over it. So in this case, both of them are kind of moving in the same direction, then there's no issue. So and in fact, like what happens is that like your augmented policy, I'm just gonna call it, will kind of will definitely be different from the one that is just training purely using the label data set, and some yeah, so there will be some path difference, and your path will be replanned in the sense. And the crucial part is this: when your policy that you're just training over your data set is recommending you to kind of go further left or further upwards into maybe hitting the wall, right? Your augmented policy, what happens is that your augmented policy, you will get like a spike in cost, and so that will just kind of drives it like downward. So you're, instead of really following the policy that your model is telling you, it will actually kind of push it back downwards towards the red path, and yeah, kind of steer it back into cost, right? And that is the plateau algorithm. Does anyone have any question on this? No? Okay.
Everyone happy with that?
Because if that's the case, then we are moving on to our next presenter.
Let's thank Yihui for his presentation.
Now I will start from this slide. So now we compare the Dagger versus GPS. So Dagger does not require an adaptive expert, which means any expert can enhance the data set so long as the states from the policy can be labeled, which means that Dagger does not care about how the data was generated, but it cares about the this data are with respect to the our learned policy, and but it has a downside, that is it assumes that it's possible to match experts' behavior up to bounded loss, which may not be always possible, such as we have partially observed domains. On the other side, GPS adapts the expert behavior. It does not require the bounded loss on initial expert. Yeah, so that's the difference between Dagger and GPS. Why do we want to use imitation learning? Because it is a combination of the supervised learning and control and planning. These two methods are quite reliable and stable. So we intuitively want to combine these two stable methods to use. And also we have the input remapping trick. As we can see from the previous slide, we train our policy given the observation instead of the real state. So which means our model, our trained policy can fit the real world or real situation, because in the test we don't really have the real states. So, but I have a question here regarding the input remapping trick, because it reminds me that that we have a similar trick, that is teacher forcing. I'm curious about whether we can employ teacher forcing in this training process, which means we randomly train our policy given the observation or the real state. I don't know whether it will works or yeah. So that's my question here. I don't know if you have any comments.
Yeah, let's discuss that for a while. I don't think we have an immediate answer, so it's a good thing for discussion. So do you want to go over what the teacher forcing does? From your understanding, it's okay. It
from my understanding, when we have a machine translation, when we predict the next word, we can randomly based on the previous gold word, or based on our previously predicted word. So that's what teacher forcing does in terms of machine translation. I don't know whether this mechanism can be employed in this training graph. So
okay,
yeah.
I'm going to try to paraphrase to understand. You're saying in, let's say, a neural machine translation system, you have a gold standard answer for the previous word.
Yes.
And you're translating the current word, not the previous word. Is that right?
Oh yeah.
And then you're using that information about what the actual previous word was to force the student model to learn appropriately. Can you be? I don't think I'm getting the translation quite right.
Yes.
Okay. So how does it fit in the framework?
So I think we can. I don't know. It will work if we train our policy randomly based on the real state or the observation, and I don't know whether it will make the training more makes the training faster, and also makes our model robust to the real world. So yeah, I don't know if any of you has the answer to this question.
Yeah.
Or maybe it's not gonna be work. We needed to train our policy purely based on the observation.
No, I think there's, I think a lot of these techniques are for robustness, right? So when you have your observations are not exactly the same as what you've seen in training, right? So you're adding noise, or you're perturbing the input, or using the input remapping trick so that you can get a level of robustness. But I guess what we've seen in most of the lectures is, you need to stay somewhat close to the current position, either within in terms of the policy or the trajectory, so as not to lose too much of your, not to go too far off track, right? That's one of the things I recall. But probably doing a completely random sample wouldn't work. I think always just some prior information that you're taking into account, and then you're doing some type of distribution locally around that area. So I'm not sure about teacher forcing in your analogy. I guess teacher forcing is saying that the previous state, now I'm going to tell you exactly where the previous state was, or I'm going to tell you not the observation, but actually where you were, all right, the actual gold state information from the previous time step, and you're going to use that to constrain, like project forward one time step, and say within that one time step from that gold standard state, which we know you were at, what's the distribution of actions or trajectories you could roll out? Is that what you're saying?
Yeah.
Okay.
Okay.
Any discussion or things that you'd like to comment on that?
Okay, so probably I continue. And the third one is it overcomes the optimization challenges of back propagating into a policy directly. As we previously mentioned, there can be a numerical instability in terms of back propagating into policy directly. So for imitation learning, this will not be a problem. And I don't think the lecturer talked very detailed in for the fourth point. I mean, usually it is sample efficient and viable for real physical systems. Yeah. So maybe we continue. And so let's talk about a model-free optimization with a model. We can just employ the policy gradient or any other model-free IL methods. Even you have already a model, and sometimes it is even better than the gradients. We can have recent analysis in this paper, but honestly, I didn't read this paper. I don't know if.
Okay, I put that paper on Slack. I found it, and you can download it if you want to look at it. I'm going to look at it, but yeah, you can go on.
Yeah. So now we talk about Dyna. So Dyna, you can view what originally Dyna is in this paper: integrated architecture for learning, planning, and reacting based on approximating dynamic programming. So I think basically we can split the Dyna into two parts. For the step 1 to 4, it basically trains a model. It basically trains a model, and for the remaining parts, we train the we employ the standard Q-learning update formula based on our trained model. So this is the idea of Dyna is actually quite intuitive, and So I don't know if I needed to explain the Dyna for each step, because I think it's quite clear for each step. Yeah,
I think it does help if some of us try to paraphrase it, because sometimes that helps other people who don't understand be able to pick it up.
Okay.
So right. So let's read it off just to be clear. So given state X, we pick an action using some type of exploration policy, right? And then we just observe the next state and what's that, tau?
No. It's the reward.
The reward.
And a reward, we get the transition, and then we update our model based on our observed state and the reward, and then we do the Q-learning update. It's a standard Q-learning update function, and next we repeat k times. We sampled from buffer. We sampled the previous states and actions from the buffer, and we do the Q-learning update. The difference between these two parts is that the first part is
which is the first part?
Step 1 to 4.
Okay.
It's based on the real experience, and the remaining part is based on the simulated
state that you do for that time step.
Yeah.
And then after doing that time step, you go through past states. And you simulate a number of actions k times.
Yes. So the difference is the source of your experience.
Right. Okay.
Yeah. This is a more general style, a more general form of Dyna. So it still contains 2 parts. For the first part, we train the model. We learn the model, and for the second part, we train our RL method based on the simulated experience. So we can see from the steps. The step 1, we collect some data consisting of transitions, and the second step, we learn the model based on the transition, based on the transitions, and then we repeat k times. We sample from the buffer. We choose an action, and we simulate the transition, and we train with a model-free IL method based on the state and the new state, the reward, and the action. And it is optional that we can take more model-based steps. Yeah, basically, it's a more general form of the previous mentioned Dyna algorithm.
So it's just elaborating on the loop. Is that right?
Yeah.
So the first version that you had on the previous slide, the action was actually done outside the loop, right?
Yes. So the first slide, it employs a Q-learning algorithm, but for this more general dyna model, it doesn't require, it doesn't mention any specific RL method. So it's it's a more general steps for the dyna style model.
So does anyone want to characterize what we mean by dyna style model in plain English? Right, we have the layout here that Weixin has given.
Okay, maybe I go on. Yes, this is an example the lecturer give to the students, which contains recent papers, and it's but actually I didn't study these two papers very carefully, so yeah, I don't know. Anyone wants to comment on this slide?
I don't think anyone will have studied the paper.
Okay.
So you know, we can put it on the Slack channel, but
okay.
If you've read it, you can give some insight. Yeah.
Okay. So yeah. This is slides I added to the entire slide. So so we can compare the model-based IO versus integrated architecture dyna. So we can see from the left side, this is a model-based IO. This is a loop, and we use our policy to act, and we get we learn from the experience, and then we train our model, and we optimize our policy based on the model. And for the dyna integrated architecture, we have another arrow that is we can employ a direct IO from the real experience. So this is a difference between the traditional model-based IO and the integrated architecture dyna. Yeah. And now I want to cover another example to demonstrate, to give you a detailed demonstration of dyna. So these figures are taken from a book named Reinforcement Learning and Introduction. And we can see from the figures, we are given a maze, and our goal is to start from a grid, and we needed to reach the final the final grid. You can see from the figure we have a start point named S, and we have the final point named G, and we needed to reach G from S. So we can see from the second figure, without planning, for the second episode, we only know we only have one error, which is the next grade of G, and if we do the planning, given that n equals to 50 times, we have for the second episode, we have already know much more information regarding the optimization policy. So yeah. Also, we can compare the difference based on the. We can also compare the difference from the first figure. So for the case there is no planning steps. It takes much longer time and much more steps for the model to how to say converge. And when we have 5 planning steps, and when we have 50 planning steps, the model can be trained very fast. It can learn how to to reach the final grid very quickly. Maybe in the second episode, it can already know how to go out from this maze. Yeah. I don't know if it's these two figures are clear to you, and if there is any comments. Okay.
So what does it mean? 5 planning steps. It means.
Oh, this means here k equals to 5. Yeah.
Does it mean the rollouts are of length 5, or does it?
Oh, it means we repeat the planning step. So k is the times for the model planning. So 5 means here k equals to 5, and 50 means here k equals to equals 50. Yeah.
In this one, you have an n here.
So
right?
maybe in the first episode, the model go from S to G, and when if we are given maybe if there is no planning step, it can only knows that if when we are at the next grid to the G, we need to go up, but it doesn't know any other information. But if we have planning steps, maybe n equals to 50, and we you see from this algorithm, we repeat k times. We sample the.
Try to point the mouse.
Okay. We sample the past states and actions from the buffer, and we can do the Q-learning update. So here in this figure, if we have planning steps, we can train our policy based on our learned model, and it will be very in the before the second episode, it can already knows much information compared with the case there is no planning step. So yeah. Because for the first episode, the model maybe go from the maze like this, and it doesn't. It only knows that we should here we should go up to exit the maze. But if we do the planning repeatedly, we can know much information. And for the second episode, here is still unknown in terms of the policy, but when the agent reach the grid here, it can already know how to go out the maze. Yeah. So that's the benefits of the diner.
So that is to say, with a larger n, getting towards the goal, when you're close to the goal, it'll be very easy to calculate.
Yes.
Yeah. But that's good in the case where I guess the branching factor of getting to the goal is getting smaller as you get towards the goal.
So yeah,
I mean, it reminds me a little bit of A-star search, how you have an h of x and a g of x, where you have the part where the agent is in and you want to try to evaluate where you're going. And then you have a g of x, which is calculating the value. How much more do you have to do something in order to reach your goal? And there's costs in both directions, right? Yeah, some bidirectional search, right? So the planning is, in at least in this maze case, is saying there's a goal state, there's a high reward state at the end. So I'm back propagating in some ways, right? The value of being in certain states, and I know which action to take in those states backwards, right? Because the larger the n, I guess, the more arrows you have populating the cells, right? Right.
So yeah, so we can see from this figure, if there is no planning step, maybe for the 10th episode, it still takes many steps to steps. And for 5, it can learn very fast. That for the second episode, it can exit the maze only using 14 steps. Yeah. And now I want to further illustrate this dynamics. When we so I want to ask you a question that what is the benefits of the dyna algorithm? Why we don't directly use a pure model-based method to maybe for this maze problem? So why do we use the integrated architecture? We have two separate. We have two parts, each of which train something based on the real experience or the simulated experience. Why do we incorporate such architecture instead of the pure model-based method?
So the question is, why don't we just use a pure model-based method, and why don't we use parts that are simulated and parts that are in the actual world, right?
Yeah.
So to clarify, like actually for the general dyna style algorithm, right? Like everybody said like this, like if you scroll back up to the general style, right? Like for the first part, right, they didn't actually update. Like so first step and second step just updates the transition.
This one here?
Yeah.
Uh-huh.
And then it didn't actually update the Q function, or it didn't actually update the policy model itself. And it only updates the policy model after you sample it. Is that right? So there's only simulated, like, here, isn't it?
It's only simulated.
Like the, okay,
so the policy is...
Yeah, the policy is updated.
Updated in simulation.
In simulation.
It's not actually updated in the first two steps, you're saying?
Yeah, which is different from dyna, which is updating the Q value update, right? If you just...
Right, in the previous slide, there were steps 1 through 4, right? And that the third and fourth step is actually updating the
fourth
policy.
and seventh steps, I think.
Ah, okay.
And if you just kind of go up like one
Go
step.
up one slide.
Yeah, the fourth and seventh step, like, so there's actually two...
There's two updates. Yeah.
Yes.
There's an update on the actual action taken, and there's the update on the simulated K times simulation.
Yeah, but in general, it doesn't update the actual.
Just to confuse things more, I'm gonna put another.
I think no. I think the entire steps are within an endless loop.
Okay.
So even for this case, the model will still update, but this is just within one single episode, I think. Yeah. So I think the model will still be updated in this. Even in this algorithm, yeah.
The policy.
It is updated, yeah, but the policy is not, right? Rather, the policy is updated, but it's only updated using your samples that you are sampling from the buffer. It's not updating it using the data that you just collected from in step 1. I mean, it can be updating that if you sample the data, but so it's not explicit on that. I'm worried if you miss that out or.
I see that dyna algorithm from another book that is it is actually wrapped in a loop. So which means the model will be updated in each episode. And for this one, it is still the model will be the model is not fixed. We can still fresh the model in each episode. So that's not fixed, in my opinion. So I don't know whether it answers your question or.
The model you're referring to is the transition model or the policy model?
Oh, I mean the transition model.
Yeah. The model is updated, but I'm talking about like the policy model is only updated within the case steps.
Can you tell me which step?
Steps. 7. Yes. Yeah. Your model VRL.
Yeah.
Like in the dyna style, right? Your step 7 it's also it's equivalent to, okay, it's also 7, but it's also 4, right?
Yeah,
so
yeah,
4
yeah.
and 7 is the same, but then like I'm saying that 4 is missing on the general view, or rather his general view. Like it's missing a queue update.
Yes.
Before you run the case step, which if that's the case, like if it's not doing the queue updates, then it kind of, you know, the whole difference between like you're updating with experience at the same time with simulated kind of doesn't really make much.
I think maybe
yeah,
I don't know if I am correct. I think learn the model already contains maybe it's equivalent to update the model and use the Q update. I don't know what it means to learn the model. So
that's the transmission model. That's the state action. And
yeah, I don't know. Okay, so I know your point.
Yeah,
That's the Q update is missing in this general style dyno. So.
Yeah.
Okay, I'm going to transition for a second to my screen and see whether we can make any sense of it. So let's see, let's put this back up. This is from Leslie Cabling's Journal of Artificial Intelligence publication. So maybe you can read that and see whether that makes sense. So it says it operates in a loop of interaction with the environment. Right, given the experience tuple, it behaves as following. Do you know the Dyna algorithm well?
No.
Okay. So we can all learn it together.
The other one.
Is it exactly the same?
This is the Q. Yeah. This is the original. This is the Dyna.
This is the original one.
Yeah, this is Dyna Q.
So this doesn't help. Okay. Come back to the slide. Sorry.
I mean, it might be just kind of missing out.
Yeah.
I have a feeling it's just missing out, right?
Yeah.
So the problem is we don't know what the general Dyna is because I didn't find any resources.
Yeah. He was saying he was saying that like the general
is not
of Dyna.
It's right. It's Dyna style, right? Meaning that
I think it would be helpful if he can give a paper link or something. I also didn't find it. Yeah.
I think he's just trying to put a couple different papers into a general framework, right? To say that you can make the rollouts long, you can make them short, you can start them from a certain part of the rollout. You know, it's sort of very. So I guess it's probably perfectly fine to add that extra missing step optionally, right? You don't have to do it, but then the question is, why do it or why not do it, right? So I guess it's not very clear. It would seem like you'd want to adjust your model based on actual experience, right? Rather than just simulated information that you're planning ahead with.
Okay.
Not that important because one update versus K update.
And you will kind of probably sample them one time or the other, right? Because you're sampling from the buffer and if you're adding it to the buffer, one of these days you're going to sample it and then you're going to run that sort of rollout.
So what's a value of K that's usually used for Dyna? I thought it was not very big.
I thought it should be like 200 or
200.
Yeah, I see this from the book. Yeah, 200. Yeah, is a reasonable. Yeah, this is 50 for the simple maze.
But that 50 is the amount of steps for planning, right?
Yes,
it's not
yes.
The K additional updates, right?
No, I think it is the K.
So the planning step is the K.
Yeah, planning step is the K.
Wait, so there's like rollout and there's like
because these two fixes are taken from the book, so maybe the symbol are different. So yeah. So I see two more interesting examples from this book I can share with you. So the first one is the environment is getting bad. So which means the barrier changes its position maybe redshift by 1 grid. And this means our previous trained policy is, sorry, this means our previously learned model is completely wrong in terms of the new environment. So one benefit of the dyno is that it can adapt itself to the new environment. It can, you see from the training steps, it can update the model. So when the environment changes, we can see from here. For the vanilla DynaQ algorithm, it takes some time for it to adapt itself to refresh the model and update the policy, and it finally can fit this new environment. It knows that this not gonna be working anymore. It need for the new environment, it should go left and then go up and then go right. So, but what is more interesting is that what if the environment is getting better? So we can see from this figure, this is a shortcut maze, which means originally we go from S like this, but now we can go faster by this way. An interesting phenomenon is that the original DynaQ probably cannot fit this new environment. It will continuously go like this. It cannot learn the new optimal policy. So there is an improvement of the vanilla DynaQ algorithm named DynaQ Plus. So basically, it's a trade-off between the exploration and the exploitation. We should encourage the exploration to let our RL method to find the new to be aware of the new environment and train the new optimal policy. Yeah, in this case, the original the previous optimal policy still works. You still can go to the final grid starting from S, but it's not gonna be the optimal solution for this case. But for the DynaQ Plus, it can fit the new environment and learn the new solution. Because you can see from this figure, it's a cumulative reward. So DynaQ Plus can accumulate some more reward within the same time steps compared with DynaQ and Dyna AC. AC here means actor critic. Yeah. So these two examples are taken from this book. I think this book is quite good. Yeah. Now we summarize the model-based IR algorithm. So for the model-based IR algorithms, it's iteratively collect more data to overcome distribution mismatch, and it's replaying every time step to mitigate small model errors. And for learning policy, we back propagate into policy. We have a Pelco algorithm, and we imitate optimal control in a constraint optimization framework, like guided policy search, and we imitate optimal control by a dagger-like process. Yeah, and we also have model-free algorithm with a model like Dyna. There are some limitations of model-based IL. The first one is it needs some kind of model. Which means it is not always available in our real world, and sometimes it's harder to train, even harder to train than we train the policy. And it takes time and data to learn the model. Expressive model can be slow, and faster model can be maybe not quite expressive. So and also there are some kind of additional assumptions such as linear reversibility, continuity, and ability to reset the system and smoothness. This kind of assumptions sometimes can be quite demanding for the real world. Yeah. This slide is taken from another slide I found it quite useful from in the web. So we compare the. I think it's more clear than the previous slides given by the lecturer. So we compare the model-free RL, model-based RL, and dyno integrated architecture. So for the model-free RL, we don't need to think about the model. We learn the value function or policy from real experience. And for the model-based RL, we needed to learn a model from the real experience. We plan our value function or policy from simulated experience. And for the dyno, we learn a model from real experience, and we then learn and plan value functions from both real and simulated experience. So I think this slide is more clear compared with the previous ones. Yeah. So here the lecturer gives an overview of many algorithms, and I don't know all of them. And basically, he categorized these methods into gradient-free methods, full online methods, policy gradient methods, and replay buffer value estimation methods, and model-based deep reinforcement learning, model-based shadow reinforcement learning. And this is a tree that we can use to determine which algorithm we can use for our model. Are you going to learn in a simulator? If yes, you need to ask yourself, is simulation cost negligible compared to the training cost? If the previous answer is no, you need to ask yourself, how patient are you? You need a faster model, or maybe you can wait for maybe several days, or yeah, you need to ask yourself such questions for determining the algorithm you want to employ in your model. Yeah, that's all.
These are good points to take. Yeah, go ahead. Anyone have something to say? I think it's good to. I mean, I like the last parts of his lecture here because he did say a lot about the big questions, which all of us I think are struggling with, right? So on the on the slide before this, he tells you a little bit about like sample efficiency, right? So
which one?
This one here.
Okay.
Right, where he says the gradient-free methods are probably the most least sample efficient, right? You need just so many 5 magnitudes more than perhaps other ones, right?
And then the computational cost is the opposite of the sample.
Right, yeah. So if you need a lot of samples, then of course the compute time for each one has to be really small, right?
I don't think he covers this algorithm in his lecture, so yeah. I didn't remember, so.
That's the at least
Did we cover this?
That's active.
Oh, that's the standard reinforced algorithm.
Okay.
Actor critic.
Yeah,
we did. And so, is the paper that they put on here supposed to be to say that to overview all of these different methods and
yes, he showed some papers.
Half cheetah, all these like points for the half cheetah problem.
Oh, I see. by using different different algorithms to do the half cheetah problem. It can take 15 days, 1.5 days, 3 hours, and 5 minutes. Depending on how many modeling assumptions you make, right? Does anyone want to discuss this slide or the next one, or the one that Weixin put in the slide deck to say that perhaps a little bit more useful is that Dinah's gluing two different sort of pull both parts together. You go over that algorithm called Pilco. Which is on your slides, right?
Oh, this one?
Backpropagate into the policy. We did Plato, right? You just did Plato. Yeah, it's on the other summary. Yeah, it's over here on the third bullet on the bottom. Learn the policy, right? Okay.
I think the idea of dagger is very similar to the active learning. I don't know whether I'm correct, because in active learning, you also have an expert for you to label the unlabeled data. And dagger, I think the idea of dagger is quite similar to the active learning. I don't know if any of you have comments.
So both are adding to your data set, right? So in active learning, you ask somebody to label data, and then you ask the person to label data that you're most unsure of, right? And you add that to your data set to improve. So with Dagger, what are you doing? You're just taking the actual simulated information and then adding it to your data set. So I think it's quite the same, right? Because in active learning, you're explicitly asking, you know, I'm really, as a student, I'm not sure about this particular instance. So I need you to guide me as an expert, right? But in Dagger, you're not necessarily doing that, right? You're just saying, I'm rolling out to a degree. I'm just going to just add it to the data set so I can get off policy information. Is that right? So I can deal with this high variance problem, right? Yeah. But it's not explicitly saying that I'm taking a state that I really have no idea about the reward about, right? I mean, I think that would be the analogous thing in reinforcement learning. Is like you get to a state, or you get to a transition, or you're making a transition, you have no idea what the output is supposed to be. Is it a good state? Is it a bad state? Did I walk into a trap, or did I find a golden chest? Right? And so you're asking the human labeler, the expert, to tell you, is it a good state? Oh yeah, it's really a good state, you know. Yeah, but both are basically increasing the size of your data set and then trying to tune Dagger is just saying, okay, because you might walk, it was the imitation learning, right? So the idea was like, if you walk off what you've already learned how to do, you will know how to recover, right? So that's the whole idea of adding these simulated pieces of information into your data set. Even if you don't have a very good Q value for them, at least you have something to grab a hold of, right? It's I would say instead of active learning, it's more like what is that other type of learning? More like semi-supervised learning, where you take some unlabeled data, you just ask your model to label it, and you say, okay, those that the model is really confident has that particular value, I just add it anyway. So for example, you know, in a classifier, right, cats versus dogs, right? I have a lot of images that are labeled as cats, some labeled as dogs. Then I go scan the web for images, and I say, is it a cat or a dog? Right? Active learning would say, I have no idea what is a cat or a dog. Please label it. Semi-supervised learning would say, I'm pretty sure this is a cat, so I'm just going to like tell it, just pretend it's a cat, right? And I'm pretty sure this is a dog, so I'm going to pretend it's a dog. So instead of being maximally uncertain, you're basically saying, without supervision, I'm just going to trust the most certain samples and add them to my data set. So I would say probably that's more like a reflection of what the algorithm is.
Because I see in the Dagger algorithm, there is no process for choosing the most valuable data for the expert to annotate. Yeah, I don't. Yeah, maybe we can improve Dagger because we don't really need useless data. Because I think in current Dagger algorithm, it will definitely generate some useless data because not each data is valuable for labeling. Yeah.
So I think that when you look at replay buffers, you want to like sample the ones where the transitions have a huge change in reward, right? So if like you're in a game and you finally kill the boss or something, or you open a secret door or something like that, then there's a huge reward value difference. Right? So when the reward value before the action and after the action is very big, then you might want to sample that more because when you encounter that, you have to really know that you are supposed to take this action, right? Yeah. So I think you're right. There are lots of times when your experiential replay will tell you, okay, well, after you take this action and before, there's no change in reward. So probably those states are not so important to sample, right? You want to get the ones where there's actually a positive change in value, right?
Yeah. Okay. Thank you.
Any other questions? Okay, so let's thank Weixin and all of our lecturers today. Okay, our class in class is getting smaller on our slides, and online it seems to be holding steady, so that's good. So we'll see you guys all next week. Thank you.
Is the video finished or?
It is going to.
I should have told you that I practiced the presentation with the presenter notes.
Oh, okay.
Yeah, so it's. So I was quite nervous because I see there is no presenter notes.
Yeah, that's the problem of not using your own laptop. But for broadcast, it's okay. Yeah. No, everyone will forgive you. As I said, it's only archived on YouTube. It's not a